So I'm going to talk about galaxy bias loops, and this is work done with Alex Egemeyer, Martin Croce, Ariel Sanchez, and Rob Smith, and in particular Alex Egemeyer, who did a lot of the MCMC work and other stuff that it's in this talk. So I'm going to talk about bias. So start with the basic description of galaxy and halo bias. So we are after the relation between tracers and the underlying density field. I'm going to work at large scales, which means I'm going to be using perturbation theory, specifically up to fourth order, so we can do the one loop bispectrum. And I'm going to assume we are primordially Gaussian and that there is no velocity bias. So under these assumptions, what we are after is a Galilean invariant set of operators which are local in the second derivatives of the potentials that relate the galaxy to density fluctuations. So let me start with the simplest example that everybody knows in bias. So let me start with the so-called local bias, local in the density fluctuations. Let me assume we're at the initial conditions. So delta is a Gaussian field. So we know basically perturbation theory, the only terms you can write are the standard terms that were written by Frey and Castañaga many years ago. So when you use this expansion to calculate power spectrum, bispectrum, etc., at loop orders, you start to see sort of divergences, which are not really divergences in the true sense, but they're highly UV sensitive, proportional to the variance of the field, that appear from what we call reducible diagrams, which are diagrams, loop diagrams that can be factorized into lower order loop diagrams. And so the parameters that you see in this expansion are not actually the parameters that you measure in the power spectrum or in the bispectrum or so on. But this is very easy to fix. So we can actually rewrite the bias expansion in what people call now renormalized way, or what we called also renormalized or multi-point propagator way, which goes back to RPT and the gamma expansion that we wrote with Martin Croce and Francis Bernardo many years ago. And basically all it boils down to is to change the definition of the bias parameters from just doing a Taylor series. Is there a pointer? From doing a Taylor series at delta equals 0 to doing the expectation value of the derivatives. And so by doing that mapping, which is fairly straightforward, you can construct the, let's see if I can use my mouse. I don't see the mouse. You can actually construct the, very straightforwardly, you can construct the renormalized expansion, which is in terms of the bias, observed bias parameters. So that's the last line up to fourth order that you see over there. And those are what we call multi-point propagators. They are basically for each, depending on the statistics you are interested in, we'll have different numbers of external lines. So if you have power spectrum, you have only one external line with momentum k. If you have bispectrum, you have two external lines, and so on. And basically, you sum all the reducible diagrams with a fixed number of external lines. And that's that object over there, the nth derivative of delta g expectation value. Okay, so the nth derivative basically gives you n external lines. The expectation value generates the reducible loops. So basically, the observable bias parameters in this very simple case of density Gaussian delta and local in delta bias is simply given by that. And what are these observables? As we know from the propagators, it's just the cross-correlation bias. So you take your proto-halos in the initial condition, and you just cross-correlate your density fluctuation with the delta field, and that gives you the V1 that appears in the renormalized bias expansion or multipoint propagator, and the same for the quadratic bias and so on. Okay, so this is sort of the basic idea, but of course bias is not so easy. It's not just local in delta. And furthermore, we are not working in the initial conditions. We want to see this at the final evolved state. So how does this expansion incorporate all these ingredients? So I'm going to use a basis which goes back to a paper we wrote with Ravi Sheth and Quan Chan many years ago. So basically, if you ask yourself, OK, let me now still be at the initial conditions where my density field is Gaussian, and I want to write the most general expression, which is local in second derivatives of the potential, then you can, for this Gaussian field, you can only form 3 rotational invariants of the density field of the say second derivatives of the potential, and those are the trace, which is delta, the quadratic combinations of the eigenvalues, which is this G2, which is defined here, which is just the second quadratic invariant, which is, oh, thank you. This quadratic invariant in the second derivatives, and then there is G3, which is the cubic invariant in second derivatives. So those are the only 3 things that you can construct, and these are the so-called Galileans also in field theory. We are in 3 dimensions, so there are only 3 instead of 4. And so basically, the bias expansion reads just at each order the possible objects that you can have out of these 3 objects, just delta, G2, and G3, and you're basically done. Okay? So you can write these 2 arbitrary order in perturbation theory. So this is what I call initial operators, because we are still in the initial conditions. Now, to make connection with the previous talk by Rin, suppose now I go from the initial conditions to the final conditions using Soldovich approximation. Okay? Then, as Rin described, and we also heard yesterday, the Soldovich approximation is just characterized by the deformation tensor. Furthermore, the Soldovich approximation is local. Each fluid element doesn't talk to any of the neighboring fluid elements. So that means that in the evolved, nonlinearly evolved Soldovich, all you need are the invariants of the deformation tensor, which is another way of saying delta, G2, and G3. So if I evolve nonlinearly by Soldovich, this will be also a complete basis of Galilean invariant bias operators. However, life is not so easy. True nonlinear evolution actually is non-local. So fluid elements talk to each other. And so we have, in addition, non-local evolution bias operators that result from the fact that the evolution of nonlinear clustering is non-local. Okay? However, we can write our basis in a very simple way, again, because remember, we want things which are local in second derivatives of the nonlinear potentials now. And again, we can take advantage of these Galilean objects, where now I can define them for two fields by just doing the quadratic combinations, so just expanding this, and then the cubic ones as well for this guy. And all I need to do now is, when I go beyond Soldovich, I need to include, say, in 2LPT, that I have an extra scalar, which is phi2, okay? And then as I go to third order, I will have an extra scalar and a vector potential, okay? And so, but once you realize that, then it's really straightforward. It's just a counting argument of, what, at third order, I can have this guy is quadratic, so this is the third order operator, okay? And then at fourth order, I just have all the possible things. So you can actually write very easily also the basis to arbitrary order in this way. So as I said, this has the advantage that these non-local operators only get generated when the dynamics is beyond Soldovich, and that has a lot of simplifications when you do calculations as well in this particular basis. Okay, but now, yeah. I what?
Are they also orthogonal polynomials?
No, so you can actually do that if you want on top of it. Yeah, yeah. So again, this is not writing the expansion with these parameters is not the parameters that you measure. So you have to write the multi-point propagator expansion by just, again, going from the Taylor series to these expectation values. Here, delta star are the initial conditions. And so basically, you write the again, you do the same trick with the basis that I just put in the previous slide. By just taking these derivatives and construct. This is really very simple. It may look ugly, but it's really very simple. You can actually do this without doing any calculation whatsoever. Just by looking at the expressions, you can basically identify. I'll give you an example later. So in connection, so for Gaussian delta, this becomes the Hermite polynomials in delta, which are orthogonal. So now the way we do this calculation is, I think it's also very simple, which is we do first this expansion at past infinity, where, so in the initial conditions where the fluctuations are Gaussian. So it is really very easy to construct this expansion in the initial conditions. And then you just evolve forward in time by gravity. And because you are evolving these proto-halos or proto-galaxies by conserving the number of objects, gravity cannot generate any new divergences. So all your renormalizations stay in place. So basically, we don't have to do any renormalization when you work in this way. So in terms of diagrams, I already say this in words, but say if this is the power spectrum, you have just the standard leading order diagram, then the one loop, the two loop. You can see also a huge advantage of this expansion is that for the power spectrum at each loop order, you should have a single diagram. Okay? One diagram at 3, one diagram at one loop, one diagram at two loops, and so on. And that stays all the way like that. Unlike in the standard way, which the number of diagrams proliferate with the number of loops. And that's because each of these guys, right, in this multi-point propagator expansion is the sum of all reducible diagrams. So all the reducible diagrams that proliferate in number when you do standard PT expansion here, they are all already summed up into observables. Same thing for the bispectrum. So there is a single diagram at 3 order, and then there are only 2 diagrams instead of 4 at 1 loop. Okay? And again, these objects are given by the sum of irreducible diagrams. Okay, so what do these propagators look like in terms of our bias basis? So the first propagator is just the observed linear bias parameter. And then there is a correction coming from the non-local evolution you get at 3rd order, which is this loop integral with a particular kernel. That is very simple. Similarly, the 2nd order propagator, which gives you the 3-level bias spectrum, is just the observed quadratic bias and the tidal, the 2nd order tidal term due to tides from the derivatives, 2nd derivatives of the potential, times this kernel, which is just cosine square minus 1 between the 2 wave modes. And then there is a loop, which is just, again, given by the non-local evolution, the same way that this one. So it's only coming from, the loops are only coming from non-local evolution. And then for the 3rd order propagator, we just need 3 levels. So I just write all the terms, the 4 terms that we have at a cubic ordering bias. So if you calculate just the power spectrum to 1 loop, which is this diagram over here, okay, I just need this guy plus this guy. So I need gamma 1 square and gamma 2 square. So gamma 1 square, gamma 2 square, and that's it. Okay? So plus some arbitrary short noise, which I'm going to call N0. So you can see here there are, you just, because this is already a loop, you only need gamma 2 to 3 orders. So there are 2 parameters here and 2 parameters there. So there will be 4 bias parameters at 1 loop plus 1 noise. So this is well known. So how well do the loops work in the case of the power spectrum as a function of k? Okay, so here we have the 4 bias parameters plus the noise. And you can see as you go to higher k, in all these diagrams, let's look at B1. So we know what the true linear bias is at large scale, so we better get that answer. And as you go to higher and higher k, you get that answer with better accuracy. You also get a good description of B2 in terms of the peak background split, which is this dashed line there. For gamma 2, again, the dashed line here is the local Lagrangian value. Okay, and gamma is not very well constrained with power spectrum alone, and this is the cubic bias, which is also not very well constrained. So, so in every plot I'm going to show here, just I have many plots for different galaxies, different halos, but let me just concentrate on galaxies which are C-mass type, like in Vous. Now the question is, okay, this has been known for a while now, so at what scale do we actually have to worry about bias loops in the bispectrum? Okay, so now I have my bispectrum, 3 order. I have the 3 gammas, a gamma 2 here and 2 gamma 1s. And then I have the 2 loop diagrams. There was, sorry, 2 1-loop diagrams. So one is gamma 2, gamma 2, gamma 2, which is this one over here. This one is gamma 3, gamma 2, gamma 1, which is over here. Okay. And now I have to also have some 0k limit terms which give you constants, which are the short noise, which are these 2 more parameters and the noise. So once you add up all the parameters, now I have 9 free parameters for bispectrum only analysis, 7 parameters and 2 noise. And that's because I'm assuming that the 4th order non-local evolution operators are absent at the initial conditions. So the way I'm actually simplifying the number of parameters, otherwise I will get 4 more, is to assume that these operators are absent at the initial conditions. Of course, when you evolve by gravity, they get generated by gravity. But they get generated by gravity with coefficients which are actually fixed in terms of the lower order bias parameters. So we will check how well this works. And I'll come back to that later to see how we can take advantage of these tricks to reduce the number of free parameters. So let's take a look at that. So now it becomes a bit more horrible, my plots, because now I have 9 free parameters. Okay, doesn't matter very much. Basically, here are the three parameters. This is the one loop parameters, and these are the noise parameters. This is by spectrum only. As I go to smaller and smaller scales, I start to constrain things better and better. Okay, no surprise there, with very reasonable chi-squares. Now, I think the question to ask is, okay, how much improvement do I get over what's known from previous work? And to sort of quantify that, I'm going to take 2 simple treatments of previous bispectrum analysis. On the left, I'm going to take the approach with the smallest numbers of free parameters that I'm aware of. That's a treatment by Hector Jean-Marie et al. For the Vous bispectrum analysis. So in that case, they assume that bias is 3-level, plus they assume it's local Lagrangian. So basically, the only 2 parameters, bias parameters, are V1 and V2. And they also assume that the noise in the power spectrum is equal to the noise in the bispectrum by a single parameter epsilon 0, which multiplies the Poisson noise. So in this model, you have 3 free parameters. The other thing that we can compare to is just do 3-level bias. Okay, so in 3-level bias, you're going to have 3 bias free parameters and 2 noise parameters if you combine with the power spectrum. So it's going to be 5 parameters. So of course, this has more parameters than this. Okay, so this is at k of 0.1. And again, to emphasize, so here I'm showing power spectrum only, bispectrum only, and then the combined. So combined should be compared with P plus B. So on the right, I'm only showing P plus B by doing only 3-level bias and doing a loop, including loops. So what you see as you march into higher k, you start to see some, for example, here in this 3-parameter model, you start to see some tension between what the power spectrum and the bispectrum want. In particular, you start to see something worrying in the sense that the bispectrum is not getting the right value of V1 of the linear bias. Okay, and also you start to see that this epsilon 0 wants to be different for the bispectrum and the power spectrum. Whereas here you see that the trees, works much better than the 3-parameter model, and the loops, of course, work even better. And as you go to, say, k of 0.2, then you see that basically this model produces a very bad chi-square. You can see the inconsistency between the different statistics and the different noises, and you start to see all these tensions. Of course, here for 3, you also see that for a 3-level bias, you start to see that there are problems, that you start getting also the wrong value of V1. But for loops, things are looking pretty good. Okay. So how does the bispectrum itself look like? So if I take my analysis from here, say for a combination of P plus B, okay, and I do the same for the loops, and I just plot the bispectrum versus the measured bispectrum, this is what it is. So this is for the 3-parameter model. So you can see the deviations of the bispectrum are of order at most 10% for the worst triangles. So this is all possible triangles up to k of 0.2. Whereas once I add the loops, in blue, you can see now everything collapses into a band which is about 2%. Okay, and you can see the difference in the chi-squares over there. So clearly, the up to k of 0.2, you definitely gain a lot by including loops. You can also ask yourself, what's the consistency between power spectrum and bispectrum when you use bias loops? So you can see here k of maximum of 0.15, power spectrum only, bispectrum only, and their combination. Basically, you see no tension between them. The linear bias converges to the right answer. You break the degeneracy between B2 and B1, which is what you expect. And you start to see some deviations of the local Lagrangian approximation for gamma 2. As you go to k of 0.2, things look pretty good still. And consistent with peak background split for B2, you see a lower tidal bias than expected from local Lagrangian, which was known from very other different works already. Whereas the local Lagrangian approximation for this ties of tides term or the non-local evolution term looks pretty solid. So the bottom line is, OK, how much do I gain by doing these things? Okay, so what is the improvement that is brought by adding bispectrum information over the power spectrum? So let's concentrate on this column, k max of 0.2. If I do power spectrum only, my error bar compared to the bispectrum is about almost 3 times as large. Okay? And this is actually the most important of all these numbers, because getting a factor of 3 improvement in B1 is what makes your sigma 8 so much better. When you add redshift distortions, your F sigma 8 so much better. Your dark energy constraints so much better. So this is the thing that really drives the cosmological constraints. So you get almost 3 times better linear bias constraint, 5 times better on quadratic bias, 10 times better on tides, and 5 times better on the tides of tides bias. Now, there are also more terms that you can add, because bias depends on matter at some characteristic scale where you're grabbing mass from. And that characteristic scale R induces terms which people call higher derivative bias that go as kr squared, kr to the 4th, and so on. And there are papers in the literature, particularly 3 papers by Leonardo, which may have talked about this on Monday, but I wasn't here, where he claims that 3 plus higher derivative bias is enough to describe the bispectrum. And so it's worth taking a look and seeing, what these terms do. An interesting thing is that if you now consider the fact that dark matter is not stress-free because of shell crossing, it gets a stress tensor gets induced. These stress tensor corrections, which is just coming from dark matter, turns out, completely degenerate with higher derivative bias. So for the power spectrum, they generate what people call a sound speed, which is degenerate with a Laplacian term times delta, which is this term. And for the bispectrum now, if you add the higher derivatives, you get 5 terms. And again, 4 are fully degenerate when you calculate the stress tensor corrections from the Blasov equation. So actually, you can just forget about the stress tensor when you include the higher derivatives. There is really no need to include any of those. So the stress tensor generates these 4 terms over here as well. So once you count, all the terms you have to add to P, to B, and for the noise, then you end up with 10 more parameters. And so the question is, do you need them? And as far as we can tell, at least for the scales we have done and the traces we have looked at, we actually don't see the need to include these terms, at least for normal galaxies of bias 2 or less. So you can see that from these two plots over here. So if you just do just 3 plus derivatives, okay, then your chi-square is worse than just doing loops with no derivatives. You can also add derivatives to the loops if you want, but you don't gain much. And also, if you combine with the power spectrum, again, the 3 plus derivatives, so ignoring the loops and including the derivatives, which are much easier because you don't have to do loop integrals, that's also worse than just including loops. Even though this has 10 parameters and this has 15, it's much better just including the loops. So how much time do I have? 10 minutes, OK. So the model I have shown so far, as I said, it's the model I call so far loops, has 10 free parameters, and the approximations that we made was in terms of the presence of operators at the initial conditions. So basically, you can list all the operators, all the bias parameters corresponding to each of the operators at 3rd order and 4th order. And to remind you, so these operators do not enter into the one loop by spectrum. You can forget them. And what we assume is for these 4 that the initial values, which are called Lagrangian here, so these constants that you see at the end, they're all 0. So that means that their final value is determined in terms of the lower order bias parameters. So that was the approximation at 4th order. And it worked pretty well. So you can ask yourself, well, can I reduce the number of bias parameters further? And if I can, will my cosmological constraints improve? So that means you have to look at the 3rd order and try to see if the same approximation of putting them initially to 0 works. So what I'm going to show now is using the time evolution that you can derive by doing Galilean invariant perturbation theory. I'm going to set this guy to 0, this guy to 0. This guy, I'm not going to get it to 0, set it to 0, because I want to compare with the same. I'm going to reduce the loops to the same number of free parameters as the tree. So I can compare 2 models with exactly the same number of free parameters. So I'm going to keep this free, but these 2 fixed. And I'm also going to use the peak background split for the cubic B3. So I'm basically 3 less parameters. So this is how this reduced now set of parameters where I just use these 3 assumptions works. First, let's do by spectrum only. Okay, and in order not to get a headache, maybe just look at B1 and look at B2 and gamma 2. And as I include smaller scales, you can see the chi-squares behave very well, and I still basically recover the same contours as I had before. If I now compare this reduced set, which is this loop with these local Lagrangian approximations, to the loops, to the full set that I described before, you see the change in chi-square is very minimal. Whereas the tree, which has the same number of free parameters and the same set of free parameters as this one, has much higher chi-square. So when combined with the power spectrum, both the tree and the loop with local Lagrangian has the same number of free parameters, which is 7. So clearly, I have a model with the same number of free parameters that works much better. So how does it work when I compare with combine with the power spectrum? You can see, again, there is no, this is really, it works pretty well. You can get, of course, narrower constraints, and everything looks pretty good. So now if I come back to how much improvement do I get compared to the previous case, so now I go from a factor of 3 improvement to a factor of 4 improvement on B1. So that seems pretty good to me. OK, so to conclude, so if you go beyond k of 0.1, basically you have to include these bias loops, and it makes your confidence in the results and that you extract about cosmology a lot more reliable. You can use time evolution of these non-local bias operators to reduce this explosive proliferation of bias parameters. So I show you an example where you go from 14 parameters to 7 parameters for P plus V at one loop, which works pretty well. And the moral of the story, if you didn't follow all the details, I presented 4 basically ways of including bias. One which has the fewest number of free parameters, 3 parameters, which is just local Lagrangian tree plus 1 noise parameter. The full tree calculation, which has 7 parameters. The tree plus derivatives, which has 15 parameters. And the loops with 7 parameters and 10 parameters. And I show this inequality. Okay? So 3 of these inequalities are trivial in the sense that, OK, I add more parameters. This is better than this. And this is better than that. But this has the same free parameters as this one. Is a lot better. And this one has a lot more free parameters than this one, and it's worse. Okay? So my conclusion from this is you can forget about that, and this one you can just replace by that. Okay? And you can keep exploring. We haven't really finished exploring. You can try to be more aggressive and try to see if you can reduce this, exploring up to what K max, different tracers, and so on. OK, I'll stop there.